Hello everyone. So today is a snowing day, so we changing the in-person class to online class. So we use this lecture video instead of class lecture. So I hope it's okay to you. But anyway, like, if you have any complaint, let me know. So I try to improve. Uh, okay. Okay, so last week we just had our a midterm exam. So most of you did a good job. So I feel very happy, and I hope you can keep your excellence and you can get a good grades, and also you can something learn something useful, like you learn you can learn more about art. Okay. Okay, so at first, let's go over some problems from our exam. The first problem uh, is just I found someone got a little bit confusing to make a conclusion. So first one uh, is easy one. We just use regulation analysis, and then from our output, you try to make your decision or make your conclusion. Uh, So let's see. Let's do this. Okay. So leading data. Okay. Uh, So let's leading data, and they usually when we lead the data, we need a, we need to have a check whether the leading data okay, like successful or have some trouble. So usually we just have a check. Okay. So then we conduct the regression analysis, use LM linear model. So we set the code and sort. Okay. And we check the result. We can use summary and ANOVA. Okay. So this result from summary and this result from ANOVA. So then from those output, what can be our conclusion? So at first we say we will find our conclusion regulation equation. So use this x like a coefficient. So the relationship is like y equal 4.108 plus this coefficient multiply this sort. So this is a regulation equation, and then we can say like whether this equation or relationship is significant. So we just check this p-value. So this p-value very small, means regulation is significant. So we don't need those things because some other people, like let's say, so your job is tell other people and make other people believe you. So we just, if p-value is very small, then relationship is strong. Some people can understand that. But if you tell other people or if statistic or degree of freedom, they got confused, right? So we usually don't need to uh, to tell them those things. Only this one. And other thing is this so this p-value shows the relationship. We do have a relationship, right? So we do have a relationship is significant. Then we also need to tell other people how strong this relationship. So how strong, maybe we can check here. So we roughly we can say like knowing this x give us 45% information about y. Okay, so usually like for our conclusion we just check these three. regulation equation, whether the equation relationship is significant, p-value, significance, and strength. Okay. 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 So let's say for regulation, we say least square regulation. So this regulation, we say this is in the regulation, the axis is smallest, least square, means axis is smallest. So here we have the axis is this. This number is axis E. So here we say this residue is just the arrow, but by now people, I don't know why people prefer this residue, not the arrow. Maybe the reason the arrow sounds not so good, right? Arrow like this is just like a mistake, but this is not a mistake, right? Yeah. But anyway, so this is axis E. Okay. So axis E equals this 4.556. So we say this axis is smallest axis E. If you use other relationship, this axis E will be big. This one is smallest. So let's confirm this. Let's say, suppose I assume relationship like this. Y equal, so here exactly the coefficient 4.10 like this. So I say I just use just use the coefficient 4 plus 0.01 x. Suppose I believe the relationship like this, then let's check axis E from my relationship. Okay, so let's change this code as y, sort as x. So maybe sometime I will say I cannot find code, right? So we should tell R the code is from that data file. So we have two ways usually. We use $sign, like read code this data file $sign code, or just attach. So let's check attach. Okay, attach means just use this data file. Okay, attach means just use this data file. Then I put this variable. So by now I understand the code. Code just find the code from that data file, right? Y, X. And if we feel not, if we want to have a check whether this is okay, sometimes maybe like those assignment not okay. So let's have a check. Just check X. Okay. Okay, so this means okay, right? So we can find this y hat. Okay, so then axis E equal true y or observed y minus y hat. Observed y or true y, true data minus our assumption our expected value or our assumption. So if that difference is small, this means our assumption is okay, is good, right? So just y minus y hat square summation. Okay. So now let's check this. What this number is. So you can say, according to my assumption, axis equals this. So use regulation, axis is this. So here just confirm their axis E is the smallest. Okay. Okay. So from the exam, someone uses this law. S is E equals this, right? Let's say S is E equal S is T minus S is R. So you find S is T, S is R, then find S is, you find S is negative. So S is E, if this S is negative, you are wrong. Something is wrong. S is E cannot be negative. Okay? Okay. And so the reason may be this one, you cannot apply this formula here because this formula S is T equal S is E plus S is R. This formula just come from regression analysis, right? Not from my assumption, not from our assumption. So if we use this formula not work. Okay? But anyway, here S is E cannot be negative. S is T cannot be negative, right? Those are changement, variance. Those cannot be negative. Okay? Okay. So now check problem 3. So this is over. So this is my data, like I from my record, like I teach pre-calculus 1054. I got those data. So like we have two final exams, part 1, part 2. So at first we need to put them together. Okay. So here we use this. Okay, we produce a new variable. Let's say we want to put a final A and final B together as final. So let's check. So I don't want to write down the long name. Like this data file was $, final A, $, final B. So I just try attach. Okay. So I put the final A plus the final B as the final. Okay. And then I have a check. But I found final A, no final A, no final. Right? So the reason is here we just only do this, the final A plus final B equal final. But this final do not put in the data. Right? We do have final. Let's check this final. Okay. We have those final, right? But we do not put those final in the data file. Okay. So if this, in this case, attach doesn't work. So we have to use this, use this $. Okay. So let's check this. So we put a final in the data file, right? Okay. So now our purpose is just try find whether final score related to the previous exams. So we use ALM regression model. Okay. So we just use this for model. This. Okay. And okay, so maybe we, okay, so here we just find S is E. So if we just only find S is E, we can use this, like these results, like regression results, residue square summation, right? Okay, so we can this SSE. So we find this SSE is very almost zero. Like negative 27 means this SSE equals 0 or 2.6. Oh, 0.000, we have 27 zero. So this is almost the zero. So we say SSE, let's say, almost equals zero. This we can say this is zero. So in R, we cannot have exact zero. So we can regard such number as zero. So S is equal zero. What does this means? Final score is completely determined by others. So here actually we final exam score equal final A plus final B. Right? Final score is completely determined final A plus final B. But this result is not what we want. Right? This result is not what we want. So actually final A, final B, just final. Okay, so here we have some trouble. Like we should, once we have final, we should delete final A, final B, or we cannot use this. We cannot use this. We cannot set the final A, final B as predictors. Okay. So now the problem we want to find, this full model and reduced model. So suppose reduced model is we just use final score related to exam 2, exam 4. We just remove exam 1, exam 3. So the question just like that. Can we in the model can we remove exam 1 and exam 3? Or exam 1, exam 3 have nothing to do with the final score? But anyway, we just use this reduced, and we find this is E. Okay, so this is 39. This is this. So this is 0, and this is this. But we say this is equals 0 make no sense. Yeah, right? But if we use this, let's say, if we use this to make, so we have mistake here actually. We have SSE cannot be 0. So if this equals 0, then we have trouble. Let's say, so our purpose here, we just want to answer this question. Can we reduce exam 1, exam 4, exam 1, exam 3 in the 4 model? So before we move further, let's say we say yes. Actually, we can remove all of them, right? Because like if the final or original model, if final related to, we just need the final equal final A plus final B. No need for exam 1, exam 2, exam 3, exam 4, right? So the question should be, if we remove these two is okay? Answer should be okay, right? Actually, remove all is okay. Okay, so let's confirm this. So we can check ANOVA for 4 model. Let's say, we just check a 4 model. Okay. Okay. So this is for from form order. So from form order, so we can find this axis E equals 0. So if we use 2 decimals, that's just 0, right? 0.00. Okay. So we say if this axis equals 0, then we can say like this p-value, all those p-value very, very small. All those p-value very, very small. And those f values very, very big. Like what is E plus 30? Means like 6.3 thing multiply 10 this power. So this is too big. So actually, like such a result is meaningless. Okay, so we cannot based on this to make our decision. So if we based on this make our decision, we say, oh, final relative exam 1, yes. Relative exam 2, yes, right? All are yes. But we say we cannot use this. So I also give us a warning message. This says ANOVA test or ANOVA F test is a perfect fit. So the perfect fit are not unreliable. You cannot unreliable, not reliable. Okay. Okay. So we say, so if we have make a mistake here, then all the way down, like all those things, all those things are wrong. So let's do this. So someone give me this, right? So, oh, okay. We so what is this? Degree. Oh, so the degree we I forget this line. Degree of freedom says the 14. So where the 14 come from? 14 is from here. Degree. So this is degree of freedom for SSE, right? So degree of freedom. Degree of freedom. This is 18. So then I can do all those degree. So those just use the formula, right? What is F value? F value is S is E reduced model minus S is 4, then divided by degree of freedom. So denominator is S is E 4 model over degree of freedom. So F value is just the numerator divided by denominator. P value is just the PF 1 minus. So the P value equals 0. F value is too big, like 5 E30. E30 means 10 30 is power. 5 0 0 0 0 30 zeros. So make no sense, right? Okay, so here actually like so for such a problem, so we should delete final A, final B. So before we can do regression analysis. So those things we call data cleaning. Data cleaning. So data cleaning, if the data have some mistake, we want to check the data first, collect those mistakes, like some typo mistake, like some, and also other one is we should remove those repeated variable. So let's say, suppose we want to check why the relationship y related to x1 or x2 or x3. So if x3 and x2 are exactly the same, then we don't need to include x3, right? So if we use regulation, we say if we say y and x2, we check whether y related to x2. The answer may be yes. So check y related to x3. Answer is yes. Y related to x3. But if we use this y related to x2 plus x3, then the R will tell us, oh, x3 we can remove, or x2 can remove maybe. So here we have some confusing. So here say x3 do related to x, do related to x, do related to y, right? But here it says x3 do not related to y. So here it will give us some confusing or contradiction. So why here we can remove x3, because if we include x2, we don't need include x3, right? But if we do not include x2, only x3, we say y and x3 have some relationship, right? Okay. So from the step AIC, find the best model, we can determine this. If we include x3, then no need to include x. If we include x2, no need for x3, right? Okay. So in step AIC, how I can judge this? I just this, like here, like 4 model. So we check we regard this 4 model, and we just check compare this model with this, or with, like suppose like with 4 model reduced model. So here, if we remove x3, we find no much information lost. Then we make this conclusion. We say, oh, x3 can be removed. So the other way is we can use correlation, or correlation or covariance. So we say like, if so covariance, we can check their linear relationship. Like if x3 equal a plus b times x2, then we say x3 and x2 are the same. If we know x2, we know exactly x3, right? So here a and b is a constant, no information. Okay. So this covariance is also an important notation in statistics. So what is the definition for covariance? So if we regard it as 2 variables, so we covariance of x and y equal ex times y minus ex multiply y. So this is definition for covariance. So here for x and y, the variable landing variable. So we have their distribution. So we can do some calculating, find this. And then covariance is we just want to make those number, like standardize this number, make this number from -1 to +1. So we just divide by sigma x multiply sigma y, or multiply divide by standard deviation for x and standard deviation y. So we find that if y and x has a positive relationship, like if b is positive, like y equal a plus bx, then correlation between them is +1. If b is negative, then correlation is -1. So other correlation is just between -1 to +1. So at those two ending point, we say the perfect relationship, correlated. So if there's covalent equals 0 or correlation equals 0, then we say instead we say x and y are independent, no relationship. Okay, so this definition for, we can say that this is for populations definition. So from sample, from data, so for data's covariance or correlation, so data is like x, we have like x, x1, x2, x3, like xn, we have this data. So y, so y1, y2, y3, we have this data. So how can we check their correlation or covariance? So we have this form is equal to xi minus x bar multiply yi minus y bar, so divided by, so this divided by n minus 1. So this n minus 1 again is degree of freedom. So we already know this, like xi minus x bar multiply yi minus x bar. So sometimes we denote this as xy, right? So we also can use regard like this. Okay, as xy over n minus 1. So let's confirm this. So let's say, suppose we have this x and y. So those are just data. We find covariance. So in R we have the simple function of COV. Let's say COV xy is this. And we also can check a covariance. Oh, I put it to here. Yeah. So COV is a covariance, COR correlation. Okay. So those things are quite the same. Just we say standardized, right? Correlation is standardized for covariance. We just change this number between -1 to +1. Okay. And so let's confirm. Let's say let's check this. Let's confirm this. Let's say use confirm this form. So how can get this number? Covariance xy is -1.75. So we can confirm this. We say summation x minus x bar multiply y minus y bar. So this should divide by Michael. So divided by divided by equivalence divided by, so n minus 1 degree of freedom. So here n is 5, we have 5 points, right? Sample size 5. So here divided by 4. So now let's check this. Okay. So this covariance calculated this way. Yeah. Okay. Okay. So instead we define, if for these two variables, if covariance equals 0, then we say they are independent. So for in real situation for data like x, y, their covariance cannot be exactly it cannot be exactly equal 0, right? No 0 almost in real situation, no 0. Only we can say really, really small, really, really close to 0. So let's say um so how can we have like a how can say like those data independent? Data independent means no relationship. Or if we have this variable y like x1 and x2 have nothing to do with those. So a typical example for independent data is random data. So I can so we can produce some landing data. So landing data just so we let's say I can produce the landing data. So we can produce 100 landing numbers. Oh, 1,000. We can produce a certain number of landing data. So where the data come from? From normal distribution, or from t distribution, or from f distribution, right? So now let's check this. So x equal r landing number. So from normal distribution, so here produce 100, give me 100 landing numbers. So these landing numbers come from normal distribution. So normal distribution, you should tell me mean or standard deviation. So here mean is 0, standard deviation is 1. So this is standard normal, right? So for standard normal, you can put for standard normal we can forget that. So we say by default is standard normal. If we wanted to specify or means not 0, standard deviation not 1, so you need to specify here, right? Okay. So if without have those, so we have x is from standard normal. So let's have a check for x. Okay, have a check. Okay. Okay, so those we have 100 those landing numbers on data. So those just from normal. We just from standard normal pick 100 numbers randomly. Okay. So now let's say for y, I also just pick get some landing numbers. So this time I just from t table, okay, from t distribution, t. So landing number from t distribution. So here you need to tell me how many number you need, how many data size with 100. So for t distribution, you need to tell me degree freedom. So I put the degree freedom 20. Okay. Okay, so you have to put the 20, otherwise, let's say it will give me error message. Let's say, suppose I just take a y, produce 100 landing numbers from t distribution. So I will give us error message. What is degree of freedom, right? This is with no default. So you have to tell me degree of freedom, right? So put the degree of freedom 20. Okay, so now it works, right? Okay. Okay, so those x and y, those x and y have nothing to do with each other. So their covariance should be 0, right? So let's say covariance or correlation. So let's check a correlation x, y. So we can find the correlation should be equal 0. But we say cannot be exact 0. So this is like a 0.005. We can look at this correlation very very small, very close to 0. So we can say like even for very small correlation, we can say x and y are independent. Okay. Okay. So sec which problem? So we say for multiple regression analysis in R, use LM very easy. LMY related to x1 plus x2 plus x3 plus x4 very easy, right? So here this problem is we use matrix operation to to do those regression analysis. So we have the formula, coefficient formula for B is x prime x inverse, so multiply x prime y. So we just use this, not use LM. We just use this to try to conduct the regression analysis. Let's say like we try to find SSE. Okay, so and from SSE or from SS, those SS are SSE, we can find F value, we can make our conclusion, right? Find P value, F value, P value, yeah. Okay, so at the first leading data, okay, and usually once we lead in, we have a check. Head data class, yeah. We want to check the data. We want to know the data, right? Whether lead in data is okay. Okay, so that's okay. So we put the MPG as y, this as x1, this as x2. So here, let's say I use attach. So just use this, yeah, and put this as y, this as x, this as x2. Okay. So this like here x, in the formula x prime x, first column should be 1 1 1 1 1, right? So before we can say like we can produce x0 is 1 1 1 1, then make a matrix like x as like put the x0 x1 x2 together as a matrix x. So this is the one way we discussed in our class. So in the exam, I find someone give me good way, better way, or another way is we use C bind. So C bind 1 x1 x2. Okay. And so we can have a check of what is the x, right? C bind. Okay. Oh, okay. So this is perfect. Okay, right? First comes 1 1 1, then x1 x2. Okay, and we this y is put this y as this is just a name. We just use uppercase, yeah, uppercase. Then this in this formula we just split the formula, put all the formula here. The R code seems complicated, so we just put this matrix x prime x, one matrix, x prime times y is another matrix. So we say M1, this matrix Tx multiply x, M2 this matrix, then B is this matrix. So we also can have a check for B, right, if we want. So B is this matrix. So this is okay. So then x P is just this x multiplied the coefficient B. Then SSE is true y minus expected y. So we put okay. So here I find someone. It's easy for us to make a mistake because those parentheses we have to match them. If we put like this, then it will give me mistake, right? So for me, I just use this way: summation for something. So these things just this square y minus y bar square, or y minus y head square. So here just y minus yp square. Okay, so then find SSE. Okay, so here we say this summation usually work for matrix. No, I'm sorry, work for vectors, not for matrix. But because this y and yp is only like just like this matrix is a one column matrix, right? So I automatically know this. I will treat this such a matrix as vector. Okay, so let's say whether we can find SSE. So we have this perfect. Okay, right? Okay, so here C bind, R bind of related to C bind. So what is C bind means? C is a column. R means row. So let's say suppose X is thus 1, 2, 3, 4, 5. Y is thus, let's say back 6, 7, 8, 9, 10. Okay, so let's check what is the result for C bind or R bind. So let's say Z is C bind X, Y. So we can have a check for this Z. Okay, so you can see. Oh, I'm sorry. Oh, so this X, Y we use old X, Y, so not those X, Y. I just use same name. Yeah. Okay. Okay. So, but combined by column. So X thus, Y thus. Okay. So let's say if we use R bind, so you can imagine what is the result for R bind. R bind like this way: X, but one X first column, the first row, Y second row. Okay, so this is C bind, R bind. Okay, so this is also a good way to make data from vectors. Okay, so we can also use data frame, right? Okay, so those actually just from exam 1 or midterm exam. Okay, so then let's talk about let's we just several times we just F test or ANOVA, but maybe but we do not discuss in detail for ANOVA. So maybe some of you are not quite familiar with those things. So let's go over this many sample ANOVA. Okay. So let's take a short break. Then we can continue. Okay.